Good afternoon and welcome to the STS-32 post-flight crew press conference. I'm going to introduce Mission Commander Dan Brandenstein here and let him introduce the rest of the members of his crew. We'll talk a little bit about the activities of the flight. We'll share some home movies and some slides and take some questions from here and the other NASA centers following that. Dan?
Thank you, Jeff. Well, welcome to the post-flight press conference. Believe it or not, we're on time. We launched a day late, a month late. We landed a rev late, a day late. And finally, we got it together and are doing something on time. I'm sure you all remember the crew. On my right is Jim Weatherby. Next to him is Dr. Bonnie Dunbar. Next to her is Marcia Ivins. Next to her is G. David Lowe. And today we'd like to share some of the things that we saw and did with you. The most difficult part about a shuttle mission is getting a whole crew to agree upon a patch or an insignia, and we accomplished that, and we figured we were well on our way. Here we're on launch morning getting suited up. We're in the suit-up room. We run through a thorough check of the suits before we head out to the pad. And that way we preclude any problems with pressurization or anything when we get out in the vehicle. As all crews, we leave the same door and go to the same vehicle with the same folks with us. And it's something that we really look forward to.
It's about 6 seconds prior to liftoff, the main engines ignite, and you see all the steam from the water suppression system. On the left, you'll see after the SRBs ignite, the shock wave coming off to the left. There it is. Liftoff, I was pleasantly surprised that I really wasn't thinking of anything other than the systems and making sure the engines were working and all the systems were working properly. There isn't a whole lot of vibration. I was, again, happy to see that. I was able to see all the screens. I felt very well prepared by the training teams. It kind of felt like the simulator with the exception, of course, the acceleration. We had you can see some of the condensation coming off of the vehicle as we fly uphill with a negative angle of attack right there. We had a camera under the belly of the vehicle looking towards the external tank, and you can see from that very wide-angle camera the solid rocket boosters leave from the stack after about 2.5 minutes. They have separation motors that looked to me like they were pointed right at my window. So I looked back inside and looked at the rest of the screens on the way uphill. I didn't want to see rockets that big. You see some of the ice floating around as the external tank comes off after the fuel is expended. This is on orbit after 8.5 minutes. Again, from that same camera in the belly of the vehicle, kind of a unique view of the external tank going down. This is the one part of the whole system that is not recovered. It breaks up in the atmosphere and lands in the Pacific Ocean in our case.
And this is the kind of view you have from the orbit that we finally got to, about 190 miles above the Earth, traveling about 18,000 miles an hour. In fact, that's pretty much the way we saw it for most of the time we were up there. There was a lot of clouds for the entire 11 days that we were up there. First major event that we had was the CENTCOM deploy. It occurred about 25 hours into the mission. That required some people in the aft end and some people in the front end working that. You can see CENTCOM coming out. It's translating away at about 1.5 feet per second. It's rotating at about 1.7 revolutions per minute. It's 14 feet in diameter, about 15,000 pounds. About 80 seconds after deploy, there's an Omni antenna that will come out on that, and then about 6 minutes, 35 seconds later, the spacecraft will spin up to about 33 revolutions per minute. You can see the Omni antenna is out at this time. It's got a solid rocket motor on it that 45 minutes after deploy will initiate its journey on up to geosynchronous orbit. It actually took several burns to get it all the way up there. And as I said earlier, CENTCOM is up on orbit right now. It's being checked out, and so far everything is looking good.
LDEF satellite, of course, had been at this time flying for 5.5 years all alone, gathering data. We came along and disturbed its peace. We tried not to disturb it too much. We had been training for the rendezvous for about a year, and I just didn't believe it was really going to be there, and suddenly it appeared, and it was in the correct position. Flew the first part of the rendezvous from the forward part of the cockpit. Then we'll float back to the aft part to perform the final part of the rendezvous visually looking out the overhead windows.
What we're using in the aft station, we have controls much like the forward station. For the rendezvous, essentially all we use is a translation hand controller, which you may not be able to see in this view, but it's under the left hand and it gives you translation in 3 axes. For sighting on it, we have a COAS or a reticle that is placed in the overhead window, and it's right above my head there, and you'll see me peeking through it periodically, but that gives you the ability to fine-tune your alignment. Here we're past the velocity vector and coming up towards the R bar or the radius vector on top of the LDEF. We didn't really get any shots as we approached it during the night, but here we're downwind pretty close during the daylight portion and trying to bring the arm and the end effector camera up in the position where we can see the grapple fixture and target.
I'm at the aft station on the right there, controlling the remote manipulator system. I have both a translational hand controller and a rotational hand controller, and actually fly the arm very much like an airplane. There's a camera on the end of the end effector, and it displays its view to the monitor, and I think some of you probably saw that on the downlink. Again, Dan did an excellent job of getting me right there in the vicinity, so all I had to do was rotate the end effector about 180 degrees to align to the target, and using a vernier rate come in and make the grapple. Got over the pin, pulled the trigger. Everything worked correctly. We got all the right indications that we had a good grapple, and as soon as we made contact there and closed the snares, then we put the brakes on. You can see that's the target that we aligned through the camera, and we've made close contact. That's the snares closing. It'll eventually rigidize the payload against the end effector, and then we have the brakes on. From this point on, then we went into the photographic survey. First, I started positioning the LDEF over the center of the bay to protect it. Jim went ahead and started his maneuver, and Marcia started taking pictures of those individual trays.
The data that they wanted was our perceptions of how this thing looked, and also photographs of each one of the trays of the 57 experiments on there. And so in about a 3 or 4 hour period, I figure I probably shot 700 frames of 70 millimeter film, documenting each one of these trays under different light levels as Bonnie rotated it on the arm around its different positions.
And here you see the berthing sequence. We took everything very slow, very carefully. The payload is 14 feet in diameter, and the payload bay is 15 feet. So we lined it with the payload bay, rotated it around, and put it down in the latches. And as the sun sets, we have it securely placed in the payload bay, and we have recradled the arm. It was the end of that day.
The one experiment that we did on everybody every day is this American Flight Echocardiograph experiment. And this looked at an ultrasonic image of the heart. David and Bonnie and I were operators, and so we did our own echoes, and then we would operate on Dan and Wex. Here's David doing himself here. We sort of all had learned in training where the particular spot was where your heart ought to be, and the heart shifts around a little bit in space, so we had to go looking for it. This is the image you get on the screen, and then we bring this data back, recorded, for the investigator, and he makes measurements of this to determine how the heart changes.
This is me actually inside the lower body negative pressure device. And again, this is an medical experiment that took 3 people to work on. I was just the subject. Bonnie did all the work with the pressure regulation, and Marcia here is taking images of my heart. This is a candidate protocol for orthostatic intolerance. This is Dan doing something called delayed type hypersensitivity. That's it's something that is essentially like a TB test that you put on, only there are 72 little needles in there. And it's to determine if the human immune system has a different response in the weightless environment. We tried to time this perfectly so that we would do this 48 hours prior to landing, and then the principal investigator would read or actually analyze the results once we got back. However, we had a wave off of 1 day, and so Dan had to be the investigator and analyze it the night before we actually did come home. It really looked much worse than it really is. This is the interocular pressure measurement DSO. We're measuring the interocular pressure of Bonnie's eyeball right here. This is, again, to test the fluid shift, to see how the fluid shift affects the pressure in the inside of your eyeball. This is Jim Weatherby doing the salivary pharmacokinetics of scopolamine and dextroamphetamine, which is just trying to understand a little bit better how drugs are absorbed, distributed, and eliminated from the body. He took some Scope-Dex, and then over a period of time, over every 30 minutes or hour or so, he had to swab a cotton ball in his mouth and collect the saliva and put that in there, and that's going back to the investigators.
We did have a little bit of in-flight maintenance to do. We found some water down in the bilges one day. We're using the free water disposable system to slurp up some of the water. We put a fix on it, and we'll show you this a little bit better in a still photograph to keep the water from getting away in future times. And periodically throughout the mission, we had to go down and do that.
This is the protein crystal growth experiment. And on day one, we activated it and then looked at each of the droplets, and this is how the crystals grow in each one of those droplets there. There's nobody home there. On day last, when we deactivated it, we go back to rephotograph what is growing in the crystals. This is not the normal way one would take pictures of things, but in space it worked fairly well. And now you can see that there is some crystal growth in these droplets. We don't know yet the results of their experiments. The FEA experiment grew a different sort of crystal. It's a fairly large one, and again, we looked at it for disturbances. This is an indium crystal, this whole tube here, and that disturbance is during an RCS burn during the rendezvous. So we brought back a lot of good data about the disturbances in micro G. And this is an experiment we ran every day or most of the days. This is the bread mold. There were some, he was looking at the effect of both gravity and light, or lack of gravity and lack of light, on the circadian rhythm of his test subject here. And so the ones wrapped in red didn't see a light pulse, and then there were some clear tubes that did see a light pulse. We marked the growth front basically in each of these tubes, and then we photographed them up close. Since they continue to grow as the days go by, he wanted to see what would happen on day 7 and day 9 and day 10. And this is basically what it looks like inside. This is 7 days in the life of bread mold. Here, each one of those thick bands is a day, which is about 22 hours for this particular test subject. The IMAX camera is not your standard camera. It weighs 85 pounds when you're on Earth, and it's fairly large. The film is 3 times wider than normal movie film. Took a little while to load, and you can see it's fairly unwieldy to hold, but it takes an incredible picture. We shot both indoor, which you see here, and then we shot some outdoor movies. This is an oblique view of the Namib Desert, which was one of the places we saw frequently not covered by clouds. We carried a number of other cameras and did a fairly extensive film test. Probably carried 16 different kinds of films that we have not flown before. Carried 2 additional long lenses, an additional camera body, looking at different camera types and shutter speeds and film speeds, and trying to improve the product we bring back from space. This is a 500 millimeter lens on the Hasselblad that I'm shooting here. And that wasn't as hard to use as it looks once you get the hang of it. And again, here's a nadir view of the same desert. And you can sort of see what we looked at. We'd get some good view of dirt, and then there'd be clouds. We saw clouds for 11 days. Here I am, that's my film table in the back, with about half of my film backs and canisters and so on. This is the Panama Canal under those clouds. And again, we felt fortunate to see that much dirt. This is basically what we looked at, this sort of picture, for most of the flight. But that was okay.
Part of our medical objectives were to look at the effects of treadmill operations, or actually exercise on orbit. And we had 3 people who did routine exercise on orbit. We also wanted to see how the treadmill affected the microgravity disturbance experiment, and we didn't have transducers. We had wax here is free floating, so in order to find out what forces there were, I grabbed a hold of it, and I think we've got the directions pegged.
We wear, of course, the launch and entry suit for launch and entry. It's a big, giant rubber suit. One of the concerns I had, being so tall, they tell me that you grow a couple of inches on orbit, or a couple of percent. I really had no difficulty getting into the suit, as you can see. I seemed to fit pretty well. Once I got my hand out, Marcia was making sure I didn't bump into anything while I still had my eyes inside the suit. The neck dam that we wear kind of squishes in on your neck, and so it's very difficult to get your head through the neck dam, and then it finally comes and you have both of your ears still attached.
We didn't get any footage during the actual re-entry, but as we crossed the coast of California, they had some high-powered cameras on us that apparently got a couple shots of some RCS jets firing. And then as we got into the Edwards complex, they had an infrared camera that here has picked us up on outer glide slope. And it's, you're probably all familiar with infrared, but it just it senses the heat and not the visual spectrum. So anything that's real white is real hot, and as you see the wheels touch down, you see the instant they touch down, they heat up and they'll turn quite white. You can see here that they're in fact down. The PLT did his primary job and got the gear down, and it's real obvious there the gear just touched down. And then they cool off a little bit apparently as they roll out, and then they heat up again as you apply the brakes. From this you can see the wing leading edge, the nose, and the windows have probably retained heat the longest of re-entry. The flashes you see on top are the exhaust from the APUs, and you can kind of pick out the side of the vehicle. The hinges from the payload bay doors, which are metal and not tile, stay hot longer, and you can see the little white spots down the hinge line, and various other materials that retain or transmit the heat away faster. Is kind of an interesting view. We double back and I'll show you also the landing in the visual spectrum, only because you don't see it very long, but Edwards usually is a desert and quite dry. However, the night before we'd had fog. This particular night there was the possibility of fog later in the evening, so there was quite a bit of humidity in the air, and that's obvious as you see the condensation on the wings and coming off the wingtip vortices as you come in to land. So it's kind of a interesting and eerie sight. It's apparently watching a shuttle land at night is not a great spectator sport, because you don't see anything until the last couple seconds as you pop out of the darkness into the light. However, the spectators in the immediate vicinity report that from about 30,000 feet to touchdown you can hear it. Apparently the air coming across the wings is rough enough that it causes some turbulence and burble that gives an audio signature. And here we are, all still kind of warm. Well, we elected to stay in the suits because it was 32 degrees out and we didn't figure we needed the hassle of trying to get out of those suits and into something else, and since it was cool, it was no problem.